Hello, my name is Gennady Staskevich, and I'm here to present a paper review of automated duplicate bug report classification using subsequence matching. This paper was published at High Assurance Systems Engineering International Symposium in 2012. This paper presents a new method called FactorLCS for detecting duplicate bug reports. It's also called triaging, bug error report triaging. So, why is duplicate detection an important topic? Well, for starters, it's really important in multiple fields, like bioinformatics for ordered sequences, bug tracking in software development, issue tracking, and customer support systems. Also, legal, which is not currently was not pointed out in the paper, but I think this particular duplicate detection in court cases will be highly relevant in the near future when a lot of the systems will become online, and I think this is another interesting area that might be interested looking into. So duplicate bug detection and tracking is a critical component of open source development lifecycle. Specifically, this is the layer that connects the developers with users, and how to address various or find various bugs that normally would go undetected or get slipped through the release cycle. So the core cause of these duplicate bug reports in open platforms is that there's actually many reasons for that, but more often, most of the issues can be attributed to these particular causes: poor search features and/or poor duplicate detection features in the software that's such as Bugzilla, diverse technical background, communication skills, misspellings, users' impatience, also language complexity, as same issue can be expressed in multitude of different ways. Also network connectivity issues. So typical duplicate detection solutions are based on word frequency. The most common issues with current approaches is that language context is often ignored. Um, for example, the most common one is called term frequency inverse document frequency, and specifically it ignores completely the sentence, the semantic structure of a sentence, and as pointed out in this particular paper, they consider preservation of a sentence, or at least an attempt of preserving the context. So a sentence is not a random collection of words, but rather a well-defined sequence of intentionally placed words. So this particular effort is looking how to preserve a sequence of words, the longest common subsequence. So second problem is that as the size of the data set grows, so does the likelihood of the similar documents may be flagged as duplicates, and that frequency-based solutions also place higher value to words that are infrequent, which actually implies that misspelled words will have a higher value, or will skew the search results. So the factor LCS is actually tries to address this issue, which is a shortcoming of term frequency-based solutions. So it tries to so the hypothesis of this particular framework is that the two reports that share the longest ordered sequence of common words are most likely to be duplicates than the two documents that share the same frequency of unordered words. So to restate this in other words is basically term frequency will just try to match up documents that share a lot of similar words, regardless of order. While the factor LCS, what it'll try to do is actually tries to look not only at the words that they share amongst themselves, but actual sequence, which words appear in what sequence. So it tries to preserve the sequence. So that's the distinction. So related work. The key objective here is to classify a newly submitted issue as either primary, which this is a new and unique issue, and was never previously seen, or a duplicate, it's already been reported elsewhere. So one of the best classification methods that was submitted by Wang et al. Is by using NLP along with process execution information. So by process execution information, this means that the internal states was preserved or during the submission of the error report. So this significantly improved their match rate between 67 and 93%. But the major drawback of this, it was tested on a very small data set that only had 77 duplicates, and the performance noticeably dropped when used on a larger data set with 30 to 100 duplicate reports. And the performance dropped significantly from 67 to 93 to 53 to 69%. And also another thing to remember is that also trying to get this execution information is also a bit heavier, more intensive. And Kirkpatrick et al. Also used the BM25F similarity function to achieve 67 to 68% similarity detection rate, which is basically a version of term frequency inverse document frequency type of framework. Let's see. So the motivation to show this example, how is this particular framework benefits? So if we look at two bug reports, and these bug reports already were pre-processed, and we have a further example on what pre-processing means down the line, but essentially it tries to normalize the text so that we can have a fair chance, an algorithm can have a fair chance of determining whether the two reports are similar or not. And using the TF-IDF or using cosine similarity and the TF term frequency inverse document frequency, basically what it does is it creates essentially a vector space of term with n dimensional, where n is the number of terms, and each dimension will have the frequency of the terms in a document, and the way to compare them is to use cosine similarity. So essentially this particular two documents will result in 68% similarity. So the problems with cosine similarity is that they fail to account the semantic ordering of words, and also, as mentioned previously, the spelling errors will skew the similarity results. So to demonstrate the FactorLCS, this is the Firefox and Eclipse Bugzilla repositories were used to demonstrate. So Bugzilla is an open source bug tracking platform, and often large projects can span multiple repositories due to external dependencies. So one of the things that with Firefox is that there is an external code base that Firefox or the Mozilla, well, it depends on the Mozilla projects. So there is a shared component between Firefox and other Mozilla projects. And the Firefox bug report dataset only includes specific bug reports that were submitted through the Firefox, and excluding all the other dependencies. So this implies that some of the bugs that have primary or were designated as primary bugs, they may reside outside the Firefox actual bug repository, and will still influence Firefox. So they should be flagged as secondary, but with external dependencies. So the Bugzilla bug tracker. So the submitted bug reports are in English, containing unconstrained text, also known as free text. And as pointed out earlier, the English language is saturated with many rules and exceptions, and many different and the same issue can be expressed as in many different ways. So users' technical experience, language directly relate to the quality of their report. So pre-processing must be used to simplify or normalize the free text. So by pre-processing, what do we mean? There is a process, basically two major steps. First to stem the words, meaning that words that have different endings, like names, naming, would become a single term, like name. Remove stop words. The words that are believed to have little value to the semantic structure, to the sentence, like a, the, and so on, are removed. So this is the preprocessing steps. First thing is that the entire text gets cast into lowercase. Then the entire text, which is typically treated as a single string, gets tokenized, and by that means it's actually split into a set of strings, or a vector of strings called tokens. Then the stemming takes place. So as mentioned before, the names like plural gets truncated into what we'll see an example of this. Actually, we've seen an example, but I'll go back and show that. Then the stop words are removed, like a, the, for, etc. And then the next step is, so these were the first 4 steps are the preprocessing, and the final 2 steps are actually for comparing the reports. So the reports get compared to previously submitted bug reports, and then we compute the longest common subsequence score for each comparison pair of reports. So dataset statistics. Actually, let me go back and just show you the stemming words. So here, both reports, you can see that the words are not, well, correct English, but they're stemmed words. So like like for separator, misplaced, sidebar, and so on. You can see that the words are slightly truncated and may not look correct, but this is how Stemmer will place them, and when they're compared, they will actually match. So this is what it really improves the matching of the words. Okay, so the 2 dataset statistics. So the 2 repositories were Firefox, that was with all the reports up to March 2012, and the Eclipse for the entire year of the 2008. So the total number of primaries included in Firefox were 67,000, and Eclipse 37,000. Total number of duplicates were 30,000 for Firefox, and for Eclipse it was 4,000, and total actual numbers of detectable using the FactorLCS were 25,000 and 2,000 for Eclipse. So the total number of reports were 97,000 and 41,000 respectively for Eclipse. So what is the longest common subsequence algorithm? So it's actually a very simple algorithm that operates on set of strings. There is no machine learning involved in this LCS. It's basically returns a sequentially ordered intersection of 2 strings of inputs while omitting the non-matching terms. So basically it's a dynamic programming problem, and the solution for efficient search of the subsequence. And as we go back to the previous example, so the bolding of the words like bookmark, separate, are essentially the sequence. This is the LCS, or the terms that show up. There's actually 23 terms across these 2 documents that show up matching in a sequential order. So that's the bolding of these terms. So the LCS is the core principle behind the FactorLCS methodology. So LCS is sensitive to, one problem with LCS, it is sensitive to the document length. So the shorter document would result in higher scores. And the solution to this problem is similarly what the IDF, or the inverse document frequency in the TF-IDF or the BM25F, is to normalize using the group length, or LCS. So the term we're going to normalize it with in LCS is the match size within group weight feature. And MSWGW feature is defined as the sum of ratios of the LCS value over the size of matching documents. excuse me. The group in the temporal window, the groups in the temporal window concepts is the result of the author's earlier work. The observation was that the vast majority of duplicate reports often occur within the window of 2000 most recent reports. So the approach that FactorLCS is to compare each new bug report against all reports until 2000 distinct groups are formed. Once the milestone is reached, compare each new report against the most recent 2000 groups. And this approach addresses several factors such as rapid growth in bug repositories and exponential cost of search both in time and space. So this is really a great observation that makes or influences the results of this work, is that the windowing, this temporal aspect of looking at the 2000 most recent reports, the high likelihood of finding the duplicate for a particular bug report. And after this time frame, the chances of seeing a duplicate report for that older issue diminishes significantly, where it makes very little sense to look for, or at least very unlikely of a bug report seen after the 2000 reports. So this is quite beneficial, as we pointed it out in bullet 3. So this is the scaling formula essentially. Basically, we have sum of ratios, the LCS value, and basically n is the number of reports in the group, where CMN is basically the LCS score, or the number of match reports between report size X and report size Y. And the m, lowercase m and lowercase n are basically lengths of reports to two reports that are being compared, or the LCS score. Okay, so let's consider an example. Consider this is basically an example right out of the paper. So we have this particular example where we have a report, a newly submitted bug report called, let's call it A, and it's being compared to reports B, C, D, and E. So what we do is we're assuming there's already several groups already formed, 4 groups in our case, or 3 groups, X, Y, and Z. And we can see for the first one, so how does report A compares to the group X. So we're going to compare group X, and there are 2 reports that actually match group X, the B report and D report. And this is the formula. Basically, we're applying the formula, will result in 60 for the first evaluation. And then when we apply the same formula for report for group Y, we get a result. Oh, that should be 1100. I made a mistake. That should be 1168.75. That's the highest score. And finally, the group Z, when we compare against Z, we're gonna get essentially 50, which is the lowest score here. So this new report is the highest correlation is with group Y from here. So, but let's take there's more to the FactorLCS. Also, the authors noticed that reports or the duplicate reports often shared some of the common fields, like across 3 fields: classification, component, and product of a bug report. And each particular field, essentially, if a duplicate report, then it was very highly likely that more than one of the fields were shared. So this is the formula that shows that if tries to capture that particular scaling, if the reports are or the fields are indeed duplicate, and then the fields that match, they will get scaled by these weights, weight 1, weight 2, and weight 3. and if they're not matching the particular fields, then it's just preserve whatever that score was for that particular field, or that MSGW score. So it's just a scaling for the three fields. And considering this example to demonstrate this particular problem, so let's look at the so we have our incoming bug report A, and then we have three groups X, Y, and Z, and we're looking more specifically at the three features here: the component, class, and product. And we can see in the first report, when we compare, we get the only one feature that is actually found to be a match. So we only this second weight 2 gets scaled by, and for our particular example, we're going to assume that weight 1 equals 2, weight 2 equals 3, and weight 3 equals 4, just for simplicity sake. Then basically for the first, when we compare it against X, we get the final score of 300, and then when we compare against Y, we're gonna get, because we match on two fields, we're gonna get W1 times 168.75, and then W3 times 168.75, again because we're multiplying by first and the third weight, and in the end we're going to result with 1181 score. So similarly, we go through the final for Z, and there is no matches, so we only get 150. I think this was one of the mistakes in a paper. Had slightly different score. So let's see. So essentially, the steps for the FactorLCS algorithms are 4 steps. So pre-process the data, compute the LCS score, compute the scaling, and then compute the final scaling of for the duplicate categories. And for the evaluation, the performance is measured using the recall metric. And recall is a ratio, a number of correctly classified duplicates divided by the total number of duplicate reports in the repository. And the data set is Firefox repository, as mentioned earlier. In addition, the Firefox repository offers the ground truth for both primary and duplicate reports. The median size of all reports in Firefox repository were 68 words, with 95% of all documents having less than 200 words. And each query was limited to return 20 most similar results, just to minimize the cognitive workload of a user, and the relevancy really drops off after the 20 most similar results. So it really made no sense to include additional reports. So here we see essentially various. So these two tables try to capture the most significant features, how FactorLCS, the grouping size, the windowing, on both the Firefox dataset and the Eclipse dataset, to see how they affect the score. And as you can see, that all data. So all data is the Firefox that includes some dependencies, external dependencies, and Firefox only, that's the one that does not include dependencies. And here we're seeing that with TW, this is considering the window, the 200 or 2000 most recent reports comparison. So we can see that we get much better scaling or much better matching when we consider the time window. And here we're actually breaking up, looking more specifically at only the LCS score, just the longest common subsequence, and then we're looking at just considering the time window, and then here we're considering the entire FactorLCS, which improves the scoring percentage recalled much better. This is in comparison to other So how does FactorLCS compares to other most prominent approaches? And this is basically shows up as roughly 5% performance over other approaches. So it's statistically significant, and the other approaches most common were term frequency inverse document frequency because of the simplicity and low cost to execute it. Let's see. Actually, the TF-IDF, there is also a cost because you do have to compute a very large inverse matrix, and that's kind of computationally expensive. Let's see. Statistical evaluation. So the statistical evaluation used to assess the contribution of key components. So multi-repository projects, the experiments show that 54% had primaries within the Firefox. And group merging, also experiments showed that when group merging was enabled, it contributed to the FactorLCS score from 0.8% to 1.2% when using data set with merged reports. And also application context matters. So results in Firefox comparison figure show statistically significant improvement than the Firefox reports that contained additional reports or external reports from the other repository. So this kind of makes sense to have application specific rather than generic matching. Also, report length matters, and FactorLCS fails to produce meaningful results on short tags. So let's see, where TF-IDF makes more sense, I guess, for very short terms. Both Firefox and Eclipse bug reports datasets were large enough and realistic to validate the utility of FactorLCS framework. And high submission rates were observed for bug reports as high as 100 submissions a day, basically showing that it was fairly impractical for human operators to look through 100 reports and try to figure out if they're duplicates or not. So that was definitely burdening on the operator. So having a system that can do that for you, it would significantly improve the overall utility of this framework. And there is also significant variance in quality and consistency of submitted reports. Again, that would place additional burden on the human reviewers. And also, ground truth can change of the report status, switch from primary to duplicate type, resulting in challenging task to perform comparative analysis, where you have to remerge, create new reports, remerge everything, and then it's just much more painful to do it by hand. So, in conclusion, the detection of reports is still a relevant and challenging problem. The first approach, based on string matching for duplicate detection, and multiple factors can directly attribute to quality of recall rates. In most cases, also FactorLCS exceeded the report rates of other approaches by at least 5%. So some of the future work: investigate optimal weight value selection. So those W1, W2, and W3 weights were actually the way they were selected. They were using the simulated annealing process, which is an energy equation, probabilistic function that tries to compute the lowest energy levels, and it's also commonly used in physics and in deep learning networks, like restricted Boltzmann machines, to solve the figure out the right weights for the network. So the W1, W2 were that's another feature to look how do you optimally figure out the weight values, and they ran up to, if I recall, up to 2,000 iteration. After that, the improvements were insignificant to run further on. Also, take advantage of typographical and alternative spelling. How can that be used? It's another interesting point of view. Also, investigate how application-specific terms and specialized dictionary can be used to improve matching. Another potential work, which was not mentioned in the paper, but I think applicability of this framework would something similar like this would be towards legal or judicial reviewing judicial documents, court cases. That would be quite interesting. Okay, let's see thoughts. So my observations were basically, or at least one of the critiques were made it a little difficult to was that different data sets were utilized for comparison of the results. Also, not clear if any duplicate reports were incorrectly attributed to wrong primary report. And how much of the impact does the size of a report have on the similarity score? Um, also, there were several minor mistakes in the paper, but overall this was a good and novel contribution to the scientific community. And for questions, please email me. Email me staskivg@clarkson.edu, and on GitHub there is a source code for the in Go language. So that's kind of I still need to upload a couple more additional files to this, but like the core, the LCS is there, the stamin is there, and the stop word list that was used also there. Okay, thank you.